Good evening and welcome to the live session. Today we'll be covering week 12 and assignments, problems related to the assignment 11, which deals with the friction factors and pressure driven flows, etc. Am I audible? So let's move to the first question. A velocity profile in a fully developed laminar flow in a pipe of diameter d is given by this, where r is the radial distance from center line. If viscosity of fluid is mu, the pressure drop across length of the pipe is what? So the problem is pretty straightforward. So what is this saying is we have a circular pipe, its diameter is given, and we have to find pressure drop across the pipe. So till now, the problems that we were doing were mostly frictionless problems. So in this kind of cases, if we have frictionless problem, we do not really need any driving force if there is already a velocity present. Since nothing was uh, slowing the fluid. But right now, we are now considering uh, flows where friction is present. So what we will have no slip conditions at the two boundaries edges. Hmm. And our profile when it is like driven by pressure, our velocity profile will look something like this. So when our profile velocity profile looks like this, the viscous forces there is velocity gradients present. Hmm. So viscous forces will be there, which will try to slow down the flow field. To maintain this particular flow field, we will need to keep applying that a particular pressure. Hmm. So a pressure drop is applied, and the velocity uh, profile attains a steady state condition uh, on this pressure drop. The velocity profile that will be obtained will be dependent on this pressure drop. So we have to basically find that dependence in this question. So velocity profile is given. Hmm. So this is the shape of the profile. This inside the bracket. This is the parabolic profile that it is like this is. Uh, this corresponds to the parabolic profile. As you can see, like if you put r is equal to 0, we will have the maximum velocity, and as r increases, the velocity keeps on decreasing till when r is d by 2, which is the diameter, the radius. So when r is d by 2, the velocity is 0. And in this case, u0 is corresponds to the center line velocity, and the center line velocity will be dependent on is the it's a scale for the magnitude of velocity that is taking place in this pipe, and this magnitude of velocity this will depend on the pressure applied, the pressure drop applied. So now this is given, and we need to find the pressure drop. So how we will approach this problem? So we can approach this problem in various ways. First of all, like if we can identify that uh, like which version of the Navier-Stokes equation is applicable here, then also like we will soon be able to derive that our the uh, uh, mm, like simple uh, del P del T will be equal to our viscous terms, and our inertia terms can be neglected in this case. And since the flow is steady and it is a laminar flow. However, we can also approach it in the way we have approached our Reynolds transport theorem problem and take a control volume and analyze the forces inside this control. So, uh, so let's first talk about the integrals present in the Reynolds transport theorem. So when we take a control volume and solve problems using Reynolds transport theorem, we have two integrals as we have seen. One is the volumetric integral, which deals with the temporal derivative. So let's say we are talking about our x direction momentum. So this direction. Then this is our temporal derivative, the volume integral. So if any momentum is getting generated inside the volume, and since our profile, velocity profile given is a steady profile, we do not really have any change with time. So this term will be. Another term that we have in our Reynolds transport theorem is related to the flux. So flux of momentum. So momentum fluxes. So momentum fluxes can be. Uh, so which surfaces are important here? Not the wall surfaces. Wall surfaces, there is no flux. So this surface 1 and this surface 2. These are important. But as you can see, this velocity profile that we have is not dependent on x. It is not dependent on x. This is a r dependent profile. So if you change x, the profile does not change. The magnitude of the profile does not change. So the flux coming in from surface 1 will be equal to flux going out from surface 2. So those two will cancel each other. We can already see that those two will cancel each other. And thus, if those two cancel each other, this term will also. So what we are left with? We are left with our total force applied. So the total force applied on this fluid element, on this control volume, not fluid element, the control volume, the total external force applied will be 0. So now we have to identify what are the forces applied. So what are the forces applied here? Here, this the viscous drag, which is coming from the wall, is a very important force, as we have already discussed. It is trying to slow the fluid. So there will be a shear stress acting on the wall. So let's say this is the shear stress. And let us say the width of this control volume is dx. So tau wall into dx. Okay. Tau wall into dx. This is the fluid element. So the dx is in this direction, x direction. We also have to multiply the circumference of this element to get the whole surface. This is a circular pipe, so I have to multiply the circumference. So that will be pi into d. So tau wall into area. Area is pi d into dx. Now what is tau wall? Tau wall we already know. Tau wall is mu del vx del r, right? Del u del r, as it is already given u, where at the boundary, at the edge, at r is equal to d by. So let's calculate this. How much is this? Mu. So here already a minus sign is there. Minus. So this is 8r by d square. If r is put as d by 2, then this is minus mu 4 by 2. Right. Oh, u0 is there. U0 is there. Okay. So we can put it here. And since we have already identified the direction, we can remove this minus sign. We already know it is going to apply opposite to the flow, and that is what this minus sign actually indicates. So since we have put the direction properly, we do not need to worry about the minus sign. So if you put this here, how does this stand out? This is 4 pi mu, 4 pi mu u0. Please let me know if there is any calculation mistake. Uh, so this is my force applied uh, on the edge of the control volume, which is attached to the wall. What about this surface 1 and surface 2? There is also a force there. What is the force? It is the pressure force. Right? Pressure is the, and this pressure is unequal. That's why this pressure gradient is there. So if at surface 1, we say the pressure is some P into this dA. So dA will be uh, into the area. So the area will be pi d square by 4. The pressure at 2 will be different. Pressure at 2 will be P plus some dP, pi d square by. So this is one force, this is one force, and this is another force. So I have to equate all these three and put it equal to 0 since no external force is acting. So what I will get, I can simply write P. Okay, let me get the function. P by d square by 4. So this is equal to here P plus dP by d square by 4, and here this tau 1, which is 4 pi mu u0 dx. So if I rearrange, what I get is this dP. So pi d square by 4 is there. I have taken this term this side, so minus dP. That's why I have got pi d square by 4. I can take it on the opposite side, and this becomes 16. Pi's will get cancelled. Mu is there. U0 is there. So up to here, right? Up to here. This is yeah. So mu is
So
there,
dx
u
and d
is
square, sir.
here, dx and divided by d square, right?
Yes, sir.
Okay. So this I have got for this element dx. So now what it is said that if this pipe has a length L, what will happen? Since I can see that this is not dependent, the term that we have got in front of dx is not dependent on x. So if I just integrate, this whole thing is constant. So whatever my pressure drop is there, delta P. So a negative sign is coming because at like lower x, the pressure is higher. As the flow progresses, the pressure becomes lower and lower. So minus delta P, this is getting equal to 16 mu u0 L by. So this option D is our correct option.
Sir.
Yes,
So could you please repeat the why that flux term got cancelled? Actually, it got
yes.
voice got cut, sir.
I let's do it in the next slide. Okay. So I will use this space over here. So in these two surfaces, there is no flux. These are attached to the wall. So only in surface 1 and surface 2, flux will be there, right?
Yes, sir.
So my uh, term will be integration over the surface 1 rho Vx V dot n dx plus 2 rho Vx V dot n dx. So in these two terms, what are different? What is different? Rho is same, dA is
The
same,
vector
integration
is
dA will be same, right? Tell me.
yes, sir. One vector is different.
Yes. So this is same. Vx expression is also same. Both of their expression is u0 1 minus r square by d square by 4, right? This is my
Yes, sir.
expression. Hmm. So this is not dependent on area. So this will come out, right?
Yes,
Oh,
sir.
no. So this will get integrated upon. This will get integrated upon. So dA, I have to write it my dA as 2 pi r dr, right?
Yes, sir.
And then I have to integrate over r, correct? So this integration for both these 1 and 2, these are same, right? There is no difference in this.
Yes, sir.
Hmm. So the difference only comes here, v dot n cap. So v expression is also this, but dot n cap is in different direction. Here dot n cap is in this direction, and v is in the opposite direction. So here this will become negative, right? Here n cap is in outward direction, and v is also is in this direction. So here this is positive. So this side it is negative, this side is positive. So here one minus sign will come. Is this clear or like
Yes,
can
sir.
you see?
Got it, sir.
Yeah.
Thank you, sir.
Okay. So other everything else is same. So this will get cancelled. So only the right hand side of my the Reynolds transport theorem is there, which is the external force. So that's what we equate. Okay. Think here some like they have directly equated this, but like it can what these expressions are there can be directly derived from our Reynolds transport. So let's go to the next question then. So the next question is for a laminar flow through a long pipe, the pressure drop per unit length varies as linearly proportional to cross-section area or proportional to diameter, inversely proportional to cross-section area or inversely proportional to the square of cross-proportional area. So what we have to find is delta P by L. This is proportional to what? What is this proportional? So can you tell me? So this is something that you can like memorize because this will be there. Like again and again, you will have to use it. So some things um, you will have to like memorize. And like with use, with repetitive use, anyway you will have it fit in your mind, so that you don't have to like derive the whole thing again and again. So this is one of them. This is something that you will like you can like engrave it in your head so that you don't have to derive the whole thing again and again and do not have to recall where it comes from again and again. So do you know this pressure drop per unit length? What is with cross sectional area? What will happen?
So inversely, sir.
Inversely, which one? The first, the C or D?
So C, sir.
C. Yeah, that is correct. So this is 1 by 8. And we can see in this question. So this is 1 by d square, right? The pressure drop divided by L. This is proportional to 1 by d square. That is 1 by diameter square. And diameter square is proportional to area. So this is inversely proportional to cross sectional area. This is correct. And it will be inversely, it won't be proportional. Why? Because you can understand if my diameter is increased, my volume which is going through is increasing, and my surface area is also increasing. But what I'm trying to say is if this is there and this is there, which has a larger cross sectional like the volume is to surface ratio. So volume is to surface ratio will be higher in this case. So there will be less resistance from the wall. The wall effect will be more in case of smaller pipe. Why wall effect is important? Because wall is actually providing the frictional force, and this to overcome the frictional force we are applying the pressure. So pressure drop will be higher in case of smaller pipe because there is more friction. For a larger pipe, there is lesser friction. so a lesser pressure drop will be. So with cross sectional area, my pressure drop will always vary inverse. Okay. Let's go to the next question. So this is also a very like similar something that you like need to know. So frictional head is given. So what is friction head? So when we are talking about head, what do we actually mean in fluid mechanics?
So energy.
Head we associated with energy. Like you have heard the term head in your Bernoulli system. So if
Yes, sir.
the head is there, this means my pressure drop has taken place of the amount rho g something. Okay, so this is what like head means that my pressure drop has been is approximately this much. So for example, like somewhere you have installed some tank and it is at a height of h from where you want to like use. Hmm. So you have some tap downstairs and like at, at a height h above you have installed a tank. So what is the pressure that you expect at the bottom? You expect rho gh, correct?
Yes, sir.
If your
Yes,
tank
sir.
is h height upwards, but you will not get rho gh. What you will get? You will get something like this. Why is this coming? This is the my frictional head through the pipe. So there will be head loss through the pipe, and that is actually given by this. So this is a very important term. So this is what is enabling us to uh, calculate what will be the head loss due to my pipes. So if we take this into account, we will get the accurate pressure drop in my tap or wherever we want to use the water. So this is the expression. Hmm. And this actually depends on which kind of flow is taking place. So it may be laminar flow or it may be turbulent flow. And for turbulent flow, there are a lot of models and like things will become a little bit complicated. We will need to use charts or some like complicated formulas to actually derive what is this F. So there is a name for this F. This is called Darcy friction factor. And this, thankfully, for laminar flow, gives like has a very simple relationship with Reynolds number. So, what is this relation out of these four? What is this relation?
64 by RE.
Yes, 64 by R. So, if I know my Reynolds number, and if I can assume that my flow is laminar, so this will happen when Reynolds number is very small. So Reynolds number is if it is below a critical value, then I can assume my flow to be laminar. And if I assume my flow to be laminar, then I will easily get my Darcy friction factor using this 64 by RE expression. And then I can plug it in this and I will get my frictional head loss. So this is correct. 64 by RE. Okay. So this is what you can actually derive. So delta P by rho G, this expression comes out to be this for laminar flow. This you can derive. How can you derive this? So here, like exactly in the our first question, we arrived at an expression where this dp dx this is equal to let's move back. So dp dx this you arrived at this equation. So uh, pi this So let me just quickly where else? So let's say for a circular pipe, it's minus dp pi d square by 4. This was equal to a tau wall into pi d into dx, right? This is what we derived in our first question, question number one.
Yes, sir.
Hmm. So from here, you can easily get minus dp dx. This is equal to your tau wall into, you will get an expression. So this expression is what I was like looking for. So this is 4 and d will be in the denominator. Right, yeah, this is the expression. So from here, this is delta p. So like since this will be constant for us, same cross sectional area pipe. So dpdx is constant throughout the pipe. So you can replace this minus dpdx as your delta p divided by L. So delta p divided by L you will get, so 4 by d is there. So tau wall, if you can calculate, you can use your like expressions obtained from your simple solutions of Navier-Stokes equation. So have you done that Poisson flow? I don't remember like if you had it in any of your assignments. Uh,
Sir, I didn't attend the complete lectures of this week, sir, so I'm not
okay.
sure.
So basically, if you solve for us like this for pipe flow and laminar pipe flow, if you like simplify your Navier-Stokes equation, you will get something like this. So del square uvx del r square. And this is constant. So this is a simple second order equation, and you will get some expression like what you got in your first problem. So something like this, 4 r square by d square. So this is a parabolic equation, and this u square value you will get using this. So this some viscosity will be there, and some other terms will be there using including diameter. So from there you can get tau wall, and from there you can get this equation, this relation. So uh, so this is how you actually arrive at this 64 by R. So you can like 64 by RE is very theoretical number. So like most turbulent models are more empirical. You do experiments and then you do fitting. And some numerical methods are also there nowadays. But this you can derive from your first principles. For laminar flow, you can derive your Darcy friction factor as 64 by RE from your first principles. Let's move to the next question. Okay. So yeah, this we have discussed just now. So pressure gradients, some like pressure gradient and velocity profile, four statements are given, and we have to find out the true one. So which one of them is true?
Sir, is it A?
Yes, that is correct. So we discussed this in our like first problem itself.
Yes, sir.
Hmm. So for a pipe with uniform cross-sectional area, uh, the pressure gradient only balances the wall stress at each and every x. And since the cross-sectional area is same, this pressure gradient will same. This won't vary. So your velocity profile is constant. This won't change. This won't change. Inertia forces balances the wall shear stress. So inertia force is not there. We already saw that inertia force is not there. Only pressure gradient force is there and wall shear stress is there. Inertia force, by inertia force, what we mean? We mean the integral terms in your Reynolds transport equation. So the area integral, which is the force due to the flux, and the temporal, the volume integral, which is the temporal variation. So those two terms, both of those terms are not there actually. The pressure gradient is there and wall stress is there. So this option A is correct. Yeah. Now we have a numerical question. So a pipe of 20 centimeter diameter and length is 30 kilometers. It transports oils from tanker to the shore with velocity is given and flow is laminar. So here also the pressure gradient is there. That's why this velocity that is given. So this will be we will assume it as our average velocity, and this velocity will not change. This average velocity will not change throughout this the whole length of this pipe. So the flow is laminar and viscosity is given. So we have to find out the power. So can you tell me how can we do this? Which concept do we have to use there? So just now we were discussing what relates to our energy, right? So we were discussing what
The
relates
head.
to our, yeah, head. So frictional head relates to energy. So so finally, what we have to find out is my frictional head. This will be multiplied by rho g. This will give me power per unit volume, energy per unit volume. Hmm. So if it is per unit volume, what I have to multiply it by? I need to multiply it with some volume. So this will give me total energy, but I need power. And this volume is a very vague term here. Hmm. So I will need power itself. So power will be divided by some time. Hmm. So this thing will actually do what? What does this thing look like? This looks like my
Flow rate.
fluid volume flow. That's correct. So this is will be multiplied by q. So this is what we need. Q we know. Hmm. Q we can calculate from my velocity. So from my or velocity and diameter I can calculate Q. Uh, so rho g we know. We have to find out this HF. So HF, what is the expression for HF? So this we will have to remember. So HF is L U square.
By 2 GD.
Yeah, L U square velocity U square G D into F. And this F, it is given flow is laminar, so I can safely assume F is 64. So let's find out RE first. What is my Reynolds number? Rho u d by mu. So, uh, is rho given?
No, sir.
Rho should be given.
So rho will get cancelled now, sir, when we put in the final equation.
Rho, yeah, will get cancelled. Correct. Rho will get cancelled. So if you put here rho and here is rho, yeah, rho will get cancelled. So you don't have to worry about rho. So let's do one thing. Let's just put the equation and see. So this is my power. So let's put everything and see what is actually required. So rho g is there. HF is L U square to G D. 4 mu rho ud, and q will be uh, pi d square by 4 into u, right? So rho is getting cancelled, g is getting cancelled. So there is 8. So this is becoming 8 u square is there. So this is and this is going to cancel. I guess d is also getting cancelled, right?
Yes, sir.
D is also getting cancelled. So is this it? Pi is there. And L is there. So how much is this coming out to be?
So 7 point, is it 7.58?
Okay. So 7.5 thousand into 10 to the 3. Yes.
Yes, 7 point, I got 7.6 kilowatts.
Okay. So this is the correct. Yeah. So simplifying was like much easier for us. So apparently, like your power is not even depending on your diameter of the pipe. It is simply dependent on the length. But I guess the diameter will be there when we are talking about the velocity. So u square, in this u square, this diameter is actually hidden. So uh, the pressure applied will still be dependent on our diameter, because your velocity will be dependent on your diameter. Okay. Let's do the next question. So water flows steadily through a reducing pipe section. So if it is a reducing pipe section, will my velocity profile be same? It won't be same, right? There will be difference, because my shear stresses from the wall is getting different. So my the pressure gradient will also change. If the pressure gradient changes, my velocity profile will also change. So, a very interesting case is being presented here. So, it is said that the flow upstream is laminar. So, flow upstream is laminar, while flow downstream is turbulent. So, there is a very different kind of a velocity profile for my turbulent. So, for incompressible flow with this, determine the ratio of the velocities. Can you tell me what to do here? So, two velocity profiles are given at two different cross sections, and we need to find out the the ratios of the two velocities. So, how to do it? What will we use? We will use the mass conservation, right? Because whatever will like uh, let's say this is the pipe. So whatever goes in will go out, because this is a steady velocity. Right? There is no water accumulating inside my pipe. Whatever water I am uh, filling inside the pipe will go out. Hmm. So in the my cross section, whatever is my flux getting inside will go out as well. So simply what we have to do is use my Reynolds transport theorem for mass conservation. So for mass conservation, what is there? So this volume term will be zero. So I am not even writing this volume because there is no mass accumulation inside my pipe. So the only term that will be there is my this area integral for the flux. So rho v dot n cap v. Correct. So this is my cross section 2. This is my cross section 1. So for my cross section 1, so this is flow coming inwards. Since my normal direction is outwards and flow is coming inwards, there will be a minus sign, right? So v dot n, whenever I break this v dot n, there will be a minus sign. So what I will do, I will write this term in the right hand side. So let me write the this positive term first. So this is for cross section 2. So for cross section 2, this will be rho and v. If I put, this is the expression for v that is given. So u02 1 minus r by r2 to the power 1 by 7. And dA is there. So dA what will be the? This will be 2 pi r dr, where r varies from 0 to r2. So this whole thing, this is equal to my first cross section. So mass entering from a first cross section. So this is rho u01 1 minus r square by r1 into 2 pi r dr, and this is from 0 to r1. Is this clear?
Yes, sir.
So please do this integration. So this row will get cancelled. So and we have to find out the ratio of these two integrals basically. Since u01 and u02 ratio is being asked. So u01 by u02. So 2 pi is also cancelling out. So what we actually have to find is basically this. So let me know how much this is.
Sir, integrating the numerator is difficult, sir.
Okay. What is the denominator integration?
R1 square by 4.
This is R1 square by 4.
Yes, sir. Denominator.
Uh, yeah. So let's do the, let me create another slide on this. So first one, let me write it down. So 0 to R1, 1, 1 minus R square by R1 square R dr. So this is equal to R1 square by 4, right? This is what you are getting?
Yes, sir.
Yeah, this is fine. So next is this 0 to R2, 1 minus R by R2 whole to the power 1 by 7, right? To R dr. Mm, yeah, so the only thing that I can think of is uh, this is what they're okay. This is the property 1 by 7. So the problem here is we cannot do any substitution, direct substitution, right?
Yes, sir.
I'm just trying. Okay, and, if it doesn't work out, then we will like do it. Let's try to take this as some x to the 7 to do this. Then minus 1 by r2 dr. This is 7 x to the 6 dx. Now r dr is basically equal to minus 7 r2 x square x to the 6 dx is already there into r will be. R I can find it out from here. R is R2, R equal to R2 into 1 minus S to the 7, right? Yeah. So this multiplied by uh, R2. Let me write. So minus 7 R2 is definitely there. X to the power 6 is also there. I have multiplied an R to substitute for this. So uh, R I have found out from my initial expression. This R is becoming R2 into 1 minus x to the power 7 and dx was there. So this expression now, if I put the substitution, so 1 minus r by r2, this is x to the power 7. So if I put that, this becomes x, and r dr is this expression. minus 7 r2 square x to the power uh, 6 into 1 minus x to the power 7 dx, right? So like this is still r is equal to 0 to r is equal to r2. We can find this out. I can find this out later. Uh, so r is equal to 0, then what is x? If r is equal to 0, then x is 1. Correct. Like, are you following what I'm doing? If it is confusing, then I will repeat.
X is 1, sir.
Yeah, x is 1. So if r is equal to r2, then x is 0. Correct.
Yes, sir.
So this is this. Mm, and 7 r2 square I can write it outside, so these are constants. Hmm. And there is an x to the power 7, so this becomes x to the power 14 minus x to the power 7 dx. Is this correct? This simplification, can you check?
Yes, sir.
So now it is simple, right? Now you can do this. So tell me, what is this value? Is this correct?
Sir, I got 49 by 120 r2
Yeah.
square.
So 49 by 120. So yeah, this integration was a little bit tedious, but it can be done. You have to remember some things that you have learned it in your class 11, 12 integrations. Uh, so if we substitute here, then we can get 0, 1. So this is 49 by 120 divided by 4. 1 by 4 divided by 1 by 4. So r two square. R. So this becomes 49 by 30. And what is R2 by R1 given? 4 by 7, right? 4 by 7 square. So this becomes 16 by 14. This is 8 by 15.
Yes, sir.
This is B. Yeah. So this integration you will have to do. This integration you will have to do for this. Okay, let's go move to the next question. So steady state flow of oil in a fully developed laminar region, shear stress is what? So this we have all like done like multiple times. Can you tell me? So it is not talking about my x variation. So in one previous question we talked that like means along the pipe, along the length of the pipe, my shear stress or the wall shear stress, the frictional force that is applying, that is constant. Hmm. So here, what is asking is along the cross section. So inside the cross section, what is happening? Hmm. So we have discussed that in the pipe for laminar flow, our velocity profile is parabolic, right? Something in the form of this u0 1 minus r, sorry, r square by, yeah, r square by d square. So something along in this length. So it's parabolic. It it has its maximum velocity where at the center, and at the wall there is a no slip condition, which means the velocity at exactly the wall is zero. So this is how the profile looks like. So what about the shear stress then? So shear stress, we know this depends on my gradient of velocity. So what is my gradient of velocity? This will be this del del r, or r derivative of the x velocity, x direction velocity. So it depends on this r, del del r, this velocity gradient. It will be proportional to my viscosity. So what happens? So is this slope, is this constant across the pipe? It is not constant. If I find out del u del r, how much does that turn out to be? It turns out to be minus mu u0 uh, 8 r by d square, right? So definitely this is not constant. This is dependent on your r. So I have just taken one derivative of this. So this depends on what r. So this first statement is not correct. Maximum at center and decreases parabolically towards the pipe wall boundary. Is this correct? So when is this shear stress maximum? At the wall or at the center? So how much is the shear stress at the center? It's zero, right? If I put r is equal to zero, which is the center, this value becomes zero. So my tau wall at r is equal to zero is zero. What about at the wall? Wall I have to put r is equal to d by 2. So if I put d by 2, this value will be more than like it will be more than zero. So minus sign is there just because of the direction, but the shear stress, the magnitude of shear stress, the amount of shear stress will be higher at the boundary. Yeah, like is that clear? Is that concept clear? Because of this parabolic flow profile, my slope is highest here, right? So what is the slope? The slope is this angle. So with this axis, this angle, this is my slope, and this slope is very high at the wall. But here, this slope is basically zero. This angle is zero at the center. So at the center, there is no shear stress, zero shear stress, and at the wall there is high maximum stress. Shear stress. So which of these options is correct? Among these four options, which is correct? So option D is correct because it is zero at center, maximum towards the point. So let's discuss this question now. Consider a steady, fully developed laminar flow. of a Newtonian fluid between two stationary parallel plates, and the distance between the parallel plates is given as 2h. Then at what distance from the center line does the local velocity equal the average velocity? So, so this is a interesting question. So at what is asked here? So our velocity profile is something like this: parabolic with maximum at the center. So at some point here at y, so from center line at some point, some distance, the velocity will be equal to my average velocity. That is what is asked. So I have to find out this y. So this is the parabolic profile. So first we need to know the velocity profile. So it is given that like means y is equal to 0 is at the center line. And what is the velocity at the center line? Center line, the velocity is maximum. So I can assume this profile y square by x square. So at h, the velocity is 0. So that's why I have divided by h square. At h, my velocity is 0. At minus h, my velocity is 0. But at 0, my velocity is maximum. So this I can multiply with the center line velocity, which I can assume as something like u 0. So this is my velocity profile, the parabolic profile that I will expect when a pressure-driven flow is uh, applied. Pressure-driven flow takes place between two parallel plates of with width of 2h. So let's find the average velocity. So what will be the average velocity? Average velocity will be u dy divided by my total width, which will be 2h. So y will vary from minus h till h. So u expression we know. We can put this expression here. U0 by 2h is, can take it outside. These are constants, and I am left with just the integration. 1 minus y square by x square d. So 1 into dy, like integration dy is y. H minus h is h minus minus h, it is 2h. And y square dy integration is y cube by 3. So minus 1 by 3 h square is definitely there, and y cube is there, which is h cube. So h cube minus minus h cube, it is 2h cube. So this will be h. So 2 minus 2 by 3. How much will be 2 minus 2 by 3? Will be 4 by 3. So another 2 is there. So 2 by 3. H will all get cancelled. So 2 by 3. So this is my u average. So what is asked? What is asked is at what y my velocity is equal to u average. So to find that y, I have to equate u average. This is equal to u0 by 1 minus y square by x square, and this is equal to what we have just now found out, 2 by 3. So u naughts will get cancelled, and I will have this. So y square, this is h square, 1 minus 2 by 3. So this is 1 by 3. So y will be h by root 3. So this will definitely be plus minus because this is symmetrical in my positive y direction also. There will be a point, and like exactly symmetric to it in my negative y direction also, there will be another point where this condition will be met. So how much is 1 by root 3? It is approximately 0.577. So this option B will be the correct answer for this question. So this was the last question for today's class. So what we discussed in today's class is a very important topics related to friction factor and pressure-driven flow. And, so if there is any question regarding this topic and any other previous topics, then you can like reach out to me in the like you can reach out to me in the YouTube, or we will also have a summary class in Tuesday in our usual time. So in this summary class, we will be discussing all the problems for from all concepts that we have covered so far. So some uh, we will like do a summary of everything, and if there is any, and that is also a doubt clearing class. So like any doubt that you have, you may bring it to the class, and we will discuss them. Okay. So thank you, and I will close the session.